This video will help you find the recursive equation of any quadratic function. This video assumes that you can find the explicit equation of a linear function and that you are familiar with the concept of the second difference of a quadratic function. Let's look at a couple of linear examples along with some quadratic examples so that we can see how the two relate together and how we find the recursive equation of a quadratic function. To begin with, we have this table which represents linear data. We know this is linear data because when we check the difference between each of our y values or our function values, they are all the same as plus 14. And if we use that difference and find out what the value would be at f of 0, we can get for this set of data an explicit equation of f of n equals 14n minus 7. Let's take this equation for the moment and let's put it aside while we work on a quadratic function. Here we have a set of quadratic data. We know this is quadratic data because each one of the first differences is different from all of the others, while the second differences are all the same, which happens to be plus 14. If you will recall, we have discussed in class that quadratic functions, in terms of their rate of change, have a linear rate of change. You can see here for our linear function, the rate of change was 14. That was always equal to the first difference. So to find the recursive equation of a linear function, we simply just found the rate of change and added it to the previous function value, as you can see here. We're going to do the same thing for our quadratic function. We're going to take our first difference, which is the rate of change of the function, and we're going to add it to the previous term of our function. And if we look, this data that we've circled is the same data that was over here in our linear function. So we can take the equation for that linear data, since they are the same, and we can take the explicit equation from the linear and add it to our recursive function for the quadratic. So as you can see, you're still adding your rate of change to your previous term to get the recursive function. But because a quadratic equation has a linear rate of change, we have to use an equation for that as opposed to just a number. Here is another set of linear data. We know it is linear data because the difference between each y value is constant at a positive 2. Which means our explicit equation is f of n equals 2n minus 1. Let's now relate that to some quadratic data and use it to find our recursive function. Here is our quadratic data. We know it's quadratic data because the first difference is changing. It's never the same. But the second difference, rather, is always the same as plus 2. And again, we can see that this data in our linear example is the same as this data, which also happens to be linear data, which is something that we know is true of a quadratic and its rate of change. So to write the recursive function of a quadratic equation, we take f of n, we're going to take the previous term, which is our f of n minus 1, and we're going to use the equation that gives us the linear data, which in this case was 2n minus 1. And all we would have to do is take that first difference data and write the explicit equation for that, and then we can put that into our recursive equation of our quadratic. In this last example, we're only going to look at the quadratic data. We're not going to look at the linear data, which just so happens to be related to the quadratic data. For this data, the first difference changes. It's plus 3, plus 5, plus 7, plus 9. We know that quadratic equations have a linear rate of change, so we should be able to write an explicit function for that first difference data. That explicit equation for that blue data would be f of n equals 2n minus 1. Because when we check the difference between that data, we see that it's plus 2 all the way down, and when we go and write the explicit equation for that, we'll pretend for just a minute that our regular data doesn't exist and that this instead would be our data. And by doing that, that's how we get the explicit equation for our first difference of 2n minus 1. But the data does exist, and it's quadratic data, and we're trying to write the recursive function for that. So, the recursive function looks like this. The recursive function is always f of n equals f of n minus 1 plus the rate of change. And the rate of change for a quadratic is linear, and it's represented by that explicit equation, in this case, of 2n minus 1. So let's summarize everything that we've done to list the steps that we need to go through to find the recursive equation for a quadratic. Function. First, we find the first difference of our data and we write the explicit equation for it. Because the first difference, or the rate of change, is linear in nature, we would get some sort of equation like 2n minus 1 or 14n plus 17, whatever it takes to fit the data for the first difference. The second step would be to take that explicit equation that we find in step 1 and just add it to f of n minus 1, and that would give us the recursive equation for a quadratic function. Remember, this is all based on the fact that a quadratic function is linear in its rate of change, and we know how to write an equation for linear data.